Hi guys. I thought I would make a little video about the so-called end game. Where are we going with this, and what is this? The Cortex Media Desktop. Now, I've shown the Media Desktop a couple of times, mostly pictures. But since we're going to do an article about PM2 and working with Node.js, let's just have a look at it. So PM2 is short for Process Manager 2, version 2. Sort of a silly name, but that's what it's called. And that is a process manager, which means that it manages how you run Node.js applications or services. And it's designed for Linux, so that and it also works on Windows, but it's designed for Linux originally. And its job is to start up services with the machine, so that when you boot the machine, these services are executed and kept running in the background, just like any ordinary service. Uh, Especially 90% of the stuff that you're going to write with Node.js are server-based. You can use it for a ton of different other stuff, but it's mostly in service form. So it's designed to be a program that sort of runs in the background doing something. So let's see. PM2 list. Uh, this one simply shows, okay, what services are running at this point, or what services have we started using PM2? And here we have the QTX authentication module or service. We have the QTX core service and something called a task manager. These are the three services that are critical to the Amibian desktop, or the Cortex Media Desktop. Amibian is the code name for it, just to clear that up. If you're not active in the Amiga community, and I don't blame you, it's not for everybody, but you probably haven't heard about Amibian. So Amibian is an emulator system that a friend of mine sort of set up, which makes it really simple to use a Raspberry Pi as an Amiga. So you basically boot into the Amiga system. And based on that, I decided to create something similar at first called Amibian GS. And the idea was, okay, let's port over the Amiga emulator, etc. And that worked fine. Uh, but then I started thinking, maybe we can make something that's even better, something that's bigger. And that's how Cortex Media Desktop was born. That, hey, let's implement a full desktop using only web technology, where the desktop, the visual part of the desktop is accessible through the browser. It's rendered using normal HTML5. And then we have a back end that is also web technology or Node.js. And that turned out to work really well. We had a test project, or a sort of a prototype of it, and I'm going to show you that now. So that's where these services come in. Now, there are going to be 5 services. There's a video chat and chat, as well as a database management module. But the 3 core services are the ones that you see here. And PM2 is really simple. You have stuff like PM2 list that I just typed. You have PM2 start, PM2 stop, PM2 restart, etc. But the most important part of PM2 is that it generates startup code for you. So even if you're not a Linux user, if you install Ubuntu, for example, and you've written a service in Quartex Pascal and you want that service to start with the Linux machine purely as a server, then you would use some of the commands in PM2, and it will generate the startup code and inject that into the Linux startup system, which can be quite daunting. It can be very complex, but it does all of that for you, so you don't have to think about it. It also deals with logging, so you don't have to have a dedicated log file. I do use a log file, but you don't have to. You can log directly to the console out, or standard in, standard out. You can basically use write line to log, and PM2 will catch that and show that as a log, and also store it as a file for you, which is what you can see in this window. So let's start up the desktop. So I have that running on localhost. This is, QTX core exposes a web server, but it also exposes a WebSocket server. So the idea here is that, okay, we use a browser, simply connect to the web server, give us the index file. When the index file is loaded, it connects back to the same server using a WebSocket and establishes a secure connection that way. And then it can send, commands back and forth. WebSocket is really cool that way. It's async, it's long term, it's designed to handle messages with ease. So yeah, it's a huge topic. We can deal with that later, but let's just connect to local hosts. Uh, so the desktop is now loaded, and this is the login dialog. Just going to log in. There we go, and you can see that there was a ton of stuff that happened with reading files. Yeah, you can see the full output here. And voila, here we have a desktop. And it's a desktop that operates more or less identical to normal Windows or Linux. Uh, it tries to mimic Amiga OS. So there are some quirks that are unique for Amiga OS. For example, the path system that is used by Amiga is slightly different. It's sort of a mix between Linux and Windows. The good parts, I just have to underline that. So it's not too cryptic, and the paths are, for the most part, compatible with normal Unix, Linux paths. The difference is that you can start a path with a drive name, HD1, for example. Uh, so you can it's easy to access drives, etc. It's much easier than Windows, for example. Yeah, so we can deal with all of that later. But for now, just think of it as kind of a Linux file system. Yeah. So just like in any ordinary desktop, you can, browse files, you can enter folders, you can go out of folders, all of the normal stuff. It also recognizes file types. Right now, this is hard-coded, but of course, file type recognition is going to be separated so that you have like a file type definition file that you can edit in any like notepad or something like that. In the Amiga system, these are called data types. And there's a data type for everything. For, text file, blah, blah, blah. Also, CD-ROMs have a data type, for example. And then you define a reference to the file system that is used. So there's a lot of complicated, really clever and smart stuff. There's a reason that people are using Amiga computers 30 years after that they went out of business. And it's not just, oh, I love that old computer. It's not just nostalgia. It's also because it really is an operating system that deserves to be alive. Sadly, the legality, and they're still fighting in court over different parts of the OS and stuff like that, which is why I said, fine, just keep your old stuff. I will cherry pick whatever I like from the ideas, and I will implement it from scratch using web technology. That way, it's 100% portable. It is platform agnostic. You can run this on an ARM system, on an x86 system. It really doesn't matter. And as long as you play by the rules, as long as you write applications uh, in a specific way, the performance is as close to native as you can almost get. Of course, there will be bottlenecks. There will be some things that, of course, native is going to do better. Uh, you know, in a perfect world, we will all write applications in standard old school C, which is the fastest, right? Or assembler. But there's nothing practical about that. We need something that where we can knock out functionality quickly, which is where the Cortex Pascal comes in as a general purpose language, easy to learn, easy to use. And we have the benefit of controlling that language, where the language, the IDE, etc. It's all built so that we can control that, and we can add features that are not really a part of the language itself. Helper features for generating user interfaces, for generating this and that. So yeah, but it does recognize some file types, the most basic file types. Uh, this is a sort of a side program which simply has one function, that is to show graphics files. Um, let's see, full, yeah, so you have momentum scrolling, etc. Let's see, it also recognizes GIFs. And this is a massive GIF file. I seem to remember that it was something like 50 megabytes or something like that. No clue how they made it. But this is an HD. You can see that it's pretty hardcore. This was used as a sort of a latency test. How can we make this transfer data as quickly as possible? And again, everything is transferred over WebSocket. It's not using the HTTP server now. HTTP server is just to deliver the desktop code and whatever dependencies the desktop have. But once the desktop is loaded, it connects back to the same server on the WebSocket. And everything from then on happens over WebSocket. Another thing is that each application is hosted in its own context, its own iframe. So, and it's hosted using some of the security criteria that the browser allows. So it's basically isolated. It has no contact with anything outside itself. You can't have code, for example, running inside a window that can somehow access and alter elements on the desktop. This is, and we're using features that are not often used by JavaScript developers. So we're sort of maxing out the API here. The only way that an application can communicate with a desktop is using messages. So when an application starts up, the first thing the desktop do is it tries to deliver a message object using a message handler, ironically. But that's the first message that is sort of delivered. And when the application accepts this, it has to communicate with the desktop using the message handler that it has received. And that's the only way it can communicate. So we have full control, security control over what happens. And I'm thinking that it's smart to adopt some of the mechanisms from Android, where you have like a security descriptor, which is a large JSON file defining what a user can do and can't do, and what an application can do and can't do. And whenever the application tries to do something like access the file system, the user will be alerted, and you have to choose, do I want this application to have access to my file system, and so forth. So yeah, I can also mention, there's something unique here, and that is the application model, because it's using a hybrid application model. So you can choose between having the normal application models that we have in Cortex Pascal, where all the code is, compiled to JavaScript. It's a single file. This is loaded into the HTML file and delivered to the browser. So it's purely a browser application, right? But the hybrid model is different. There you have the program is divided into two parts. So you have one part that is designed to run server side, and it's executed as a node.js service. And it's allowed to run for the duration of the program, right? When you close, if you close the window, that the background service is terminated. The second part is the visual part. This is your user interface, the buttons and the content of the window, and that is shipped to the window in ordinary fashion. Again, over WebSocket, everything happens over WebSocket. When those two have been started successfully, the desktop keeps track of this. A channel is opened between them with the desktop and server as a sort of a middle tier. And the core service that you see here, Qtx core, takes care of all the message delegation. So if you start, for example, 3 instances of the same program, it will start three instances of the same service, and it will know the difference between them. It will also know which window sent what signal. But the front end in the hybrid application model will then be able to communicate with the backend in real time. And this is cool because then we can have stuff um, like a torrent client, right? Um, Torrent clients do require to be executed in the background on a proper machine. You can probably run a torrent client in the browser if you convert, and really go to town and work on it, but it's going to be real clumsy. So it's better to have that running as a background service. And it will be connected to your account, right? All your files are actually stored in a folder, which sort of mimics a hard disk. So you can have like 10 users, and each of them will not be able to touch the other user's files. So when you start a program, and the application requests file system, it will simply be given that folder. It will not be allowed to access anything outside of that. But yeah, with a background service running, you can deal with torrents, and the background service will send signals like, okay, progress updates. We have downloaded 10% more of file number 1, and then the user interface part will be able to display that so that it will behave, and you will have all the functionality of a native application, except that it's spread out in the cluster. If you're running a cluster, I'm probably making this a lot more complex than it is, but yeah. My point with the cluster is that these services can either run on a single machine, or you can spread them out. So if you have I can show you here, if you have built a cluster like this, for example, this is 5 Odroid XU4s, and they communicate over a switch. So they find each other. So when this one starts up, each of the services are run on a separate machine, right? So it only uses one core on a separate one, which leaves all the other cores for work. So when you start, for example, an application like a torrent client, the core will actually check and see, okay, how many machines do I have available? Okay, do I have a machine with a free core? Okay, then I will physically send the backend code there and start it up on that machine. And again, all the tunneling and all the signal dispatching between backend and front end is taken care of by the core. So it's quite elaborate, but I think it's quite elegant the way that it works, because you're able to harness the power of cheap available technology in a way that's quite different. It's clustering, hardware clustering is usually something that IT professionals do. It's something that you expect to find in a data center or something like that, not in somebody's home. So if we're able to make clustering as simple as possible so that anybody can use it, I think that's a win, and it's also very unique, especially when you can scale from a single SPC like a Raspberry Pi or something like that, all the way up to 5 monster x86 machines or PowerPC or whatever you have available. As long as it runs Node.js, you can run this on anything. So there's a lot of freedom in that. Speaking of clustering, you can have a look at the preferences. It's a little bit slow now with that 50 megabyte GIF. Also, I'm running this inside VMware, so it's not exactly top performance here. So here is an overview of the running services. These are the same that you see here, but they're also available, visually in the settings. And again, there will be more services as we see, evolve this technology, and you will be able to, start, stop, restart, to basically deal with all of them from the user interface. These haven't been filled out. Again, this is just a prototype. But the idea is that you can install software. If you've written an application, a hybrid application, for example, in Quartex Pascal, you compile it, save it out as a package, a specific package that is specific for the Cortex desktop. Then installing that software here should be as easy for the user as possible. When we have enough software going for this, we can also set up like a repository system, sort of package management system, a bit like Linux. So yeah, there's a ton of potential in this. And the fact that this is all HTML5, it's all JavaScript, HTML5, platform agnostic. It can run on anything. You can also host it on anything. You don't have to install this on a Raspberry Pi and then sort of use the Raspberry Pi to display the interface because it's web. I connected to these services using a normal browser on a normal URL and a port. So you can actually run this headless, as it's called, on a cheap ARM device. You don't even need to have an ARM device with a GPU or display settings. As long as the services start up, you can connect to that headless device using your laptop or stationary PC. Heck, I've even had it running on my television. I have a smart television with a browser capability on it. So it's pretty cool once you have it running. I can start some of the other programs. So this is an old school assembler. If you were doing computing in the 80s, you probably remember things like ASM1, CK assembler, stuff like that. This is about as low level as it gets. So here labels, machine code instructions. But the trick here is that this isn't actually 68K machine code. This is actually WebAssembly. So all of this is compiled into a bytecode format called LDEF, or language definition files, which is further converted into WebAssembly. And the idea is also to have multiple export possibilities. So, okay, we can export to WebAssembly, we can export to actual executable x86 code or ARM code, a bit like .NET. So we can assemble the code, parsing 37 lines of code, blah, 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 and then it builds the model. And it will list out the bytecodes. And we can also do a disassembly of the buffer. And you will see that this differs from the source code, by all the jump statements have calculated offsets now. So everything is, it's binary code, relative. You can also run it. There we go, and it left some values into some registers and a couple of values on the stack, which was the test. This is running completely separate. The code running inside this window have no way of talking with the outside except through messages. And it uses messages a bit like Windows API calls. For example, there are messages for registering menu items. So if I go up on the system menu here, you will see that this has a menu item which sort of is identical to the toolbar here. If I switch window, open up the system menu, you'll see that the menu is unique for each application or each window. You can also run some emulation games. This actually fires up a DOS emulator, which is converted to, I think it's WebAssembly, or is it? No, actually, this is a precursor to WebAssembly, sort of bytecodes that are executed in JavaScript. So there's a limit to how fast it goes, but it's really smooth. So they compiled DOS to this sort of bytecode system. It's called ASM.js. That's the precursor to WebAssembly, and it's really fast as well. So one play full game. Easy. Play next level. Let's go. Yeah, it even plays music. I actually remember this from I think it was the early 90s or something like that. This was, very popular on the PC. It was one of the first shoot 'em up games for the PC platform. I think it was 486 DX2 or something like that you needed, because before that, everybody was sitting with Amigas, and the PC really didn't have any cool games. It only had strategy games and point and click games, and this was the first action game that really demonstrated that the PC could become a kick-ass gaming platform. But it was mostly seen as a business machine back then. But yeah, it runs really well. Quake as well, actually, I've demonstrated that a couple of times. Quake compiled to JavaScript runs like hell. So getting like 50 frames per second and 60 actually. It actually maxed out the browser. The browser can render graphics at, I think there's a hard limit on 60 frames per second, which is more than usable. I mean, hey, you can have games running at 30 frames per second, which is perfectly playable. If games is your thing. Personally, I'm more interested in the potential in the system software and the fact that this can be installed anywhere, right? You can people who make NAS boxes or routers for that matter. If you go out and buy a router, chances are the user interface is going to be crap. So when you log onto the router, you get a static page with fiddly settings, HTML that looks like it's from early 2000 or something. Instead, they could install this. It wouldn't really cost them anything. They have everything that they need, like a small embedded Linux. Okay, install node.js, and then they can deliver this instead, which is a completely different experience. So yeah, there's a ton of stuff to talk about. I actually also managed to get Free Pascal running, Free Pascal compiled to JavaScript. I think it's in here. I didn't seem to like that, but yeah, again, this is a prototype, but I did manage to get this working. But we can deal with that later. Okay, so the point is that you can actually use this as a platform in itself when the applications are evolved enough, when people have gotten to grips with Cortex Pascal, they have gotten to grips with working with this as a platform, just like we use Delphi to create applications for Windows. When all of this is sort of become polished and common and easy to use, then we're going to see some pretty advanced applications. And also, I want to start, when Cortex Pascal is done, this one is done, it's stable, everything is good. Then we can, start on the final move, which is to make Cortex Pascal compile itself to JavaScript. Then we have sort of move the entire development cycle, all the development tools, the entire ecosystem onto web, and then it's a sort of a free agent. It you can run it anywhere. And that's when the fun begins, because then you can have teams of developers that can simply install this on some cheap hardware, use their laptop or whatever. You can have 5 or 6 guys that are working on the same team, logging into the same server, starting the same development tools, and using the platform to deliver something larger. Especially when you can start making mobile applications in QTX itself, running on the desktop. That's when the fun begins. We can start to target x86 and ARM, etc. directly. That's so yeah, it's a big dream, but hey, I think I've proven that it is possible to get there. So yeah, okay, I'm not going to spend more time on this now. We can dig into the details later. I'm going to do a build of the update now, and then upload that so that it is available. I've been spending some time on the HTTP post stuff to make sure that that works. It was a bit quirky, but we did find the solution. So okay. Cheers. I'll talk to you soon.